Hello, my name is Greg Risterman from Olympus. I'd like to welcome everyone today to this webinar titled Advances in Phased Array Scan Plan Design Using the Compound S-Scan. This webinar will demonstrate the benefits of the Compound S-Scan for weld inspection, OmniScan setup, and analysis of Compound S-Scan weld data using OmniPC. Our presenter today is Chris Magruder. Chris is a global products support specialist for Olympus phased array products. He has over 15 years experience providing global support, training, and application development for phased array customers of all levels, in addition to participating in new phased array product development. This informational webinar will last approximately 1 hour. If you have questions, please type them into the Q&A panel in the lower right portion of your screen during the presentation. The chat panel is not used. If we are not able to get to your question during the live event, they will be addressed personally either by email or phone after the presentation is over. Now, without further ado, I'd like to turn the presentation over to Chris Magruder. Chris, take it away.
Hello, everybody. Thank you for joining us. Our webinar today is about a new feature in the Olympus NDT Setup Builder that will unlock some more functionality and power in the OmniScan and Focus PX instruments. The objectives for our webinar today are to provide a basic overview of the Olympus NDT Setup Builder, explanation and overview of benefits of the Compound S-Scan as opposed to a linear or E-scan or a traditional S-Scan, explanation of procedure for use of the Compound S-Scan in current OmniScan software 4.2 that has been recently released and is on the Olympus website right now. There's a few caveats and explanations for those of you still using OmniScan 4.1 that are also explained regarding the Compound S-Scan. And most importantly, a demonstration of data examples to illustrate the benefits for weld inspection using the Compound S-Scan. The Compound S-Scan, as opposed to a standard S-Scan, is really a very simple concept in that it uses the same angular range of 40 to 70 or 72 degrees S-scans, but we are separating the exit point between focal law first and last over the entire elements of a 32 or 64 element probe. The Compound S-Scan is a combination of traditional S-Scan and a linear scan, or what the ASME calls an E-scan. The definition of a traditional S-scan would be a group of a multiple angle A-scans, typically 40 to 70 degrees or so, all being generated from the same group of elements. The definition of a linear scan would be a single angle, multiplexed, stepping 1 or 2 elements at a time through the entire probe. So the Compound S-Scan is a combination of both of those, allows the flaw characterization, detection, and sizing benefits of a traditional S-Scan while utilizing all of the elements of a 32 or 64 element probe. The result of this is that with fewer groups and fewer setup files for a range of piping weld bevels and thickness and diameter, we end up with a more efficient acquisition and analysis with fewer decisions and scan plan considerations than use of multi-group traditional S-scans and E-scans. The Compound S-Scan is compatible with any 32 or 64 element probe and wedge, but is uniquely beneficial when used with Olympus's new weld series probe models that you'll see throughout this presentation, the A32 and the A31. These two probes are designed to replace many different models of probes and wedges in different configuration to cover the most common apertures for the widest range of weld inspection bevels. The benefits of these probes include improved SNR, smaller ergonomic housing. A big improvement is the wedge models, and we'll explain a little bit more about those later in the webinar. And these are used for a wider range of calibration and improved acoustic results for typical welds. Additionally, fewer, more efficient models using the same wedges allow greater range of inspection. And the three probes that make up the new weld series probes, which would be the most common ones for a service company in their toolbox, would be a small 5L32A31 housing. This has the same configuration as the A11 or PWZ3 probe in that it's 32 elements, in this case a 0.6 millimeter pitch in different frequencies. And then the A32 housing, which comes in a large 1 millimeter pitch, 32 element configuration for heavy wall, thick vessel, large apertures, or twice as many elements, 64, at half the pitch, 0.5, that uses the same housing, thus enables use of the same wedges for a wide range of inspections. So again, the compound S-scan is compatible with all of the typical probes like the A11, A2, A12, which are very common models, but throughout the presentation we'll see some of the benefits combining of the new weld series probes and the new inspection technique. So, like I said, the compound S-scan is very simple in practice and in procedure. The main benefits are in descending order of priority is one, the inspection plan is almost always closer to the weld. In most welds up to about 25 or 30 millimeters, we're going to put the wedge face directly against the weld toe. For many of these considerations, we're removing some inspection variables that are typically either decided by the operator or by the inspection procedure, but as close to the weld as possible while still maintaining all of the coverage that we need is going to end up with our best inspection. In addition to being closer to the weld, as opposed to backing this probe up from the weld just to open up the S-scan for more coverage. As much of the first leg that we can inspect, much of the weld on the first leg that we can inspect as possible, and as close to the weld as possible, our results and sizing accuracy, characterization, and overall confidence is going to be much greater. The next benefit is more coverage. Depending on the pitch of the probe and configuration, up to 200% plus more coverage, reducing the number of groups required for a full inspection. So with fewer groups, that also means fewer setups, less analysis, easier workflow and calibration process as well. In most cases, even a single compound S-scan group for welds now over 25 millimeters is possible, practical, and results in a better inspection. So when we're talking about the compound S-scan or any inspection strategy to cover a range of weld bevels for a particular job or just your regular work procedure, fewer configuration files. When we first started implementing the compound S-scan, this wasn't an immediate benefit, but became one very quickly. The several standard S-scan configurations using common probes in different focus are adapted to different thicknesses where only the adjustment of the range, gate position, and scan sensitivity, which is typically a B31 piping notch or side drill hole for its sensitivity based on that weld bevel. And that amounts to fewer decisions, fewer scan plans, less engineering, and much more productivity. Phased array training and expertise is supposed to be about mechanical acquisition and analysis, much more so than software button pushing and who knows the ABC 1, 2, 3s of creating setup files. In most inspections, all probe elements are used regardless of the thickness. So unlike a standard S-scan, in our 32 or 64 element probes, we're generally going to program the S-scan range across the entire range of elements from the front of the probe to the back of the probe, which is a big advantage for some reasons that we'll explain. So as a comparison of a single S-scan, a single compound S-scan, and a multi-group S-scan using the same probe and wedge. In this instance, we have the high angle, typically 70 or 72 degrees, exiting the wedge very close to the dampening with the probe as close to the weld as possible. And we also want to get the full skip coverage from the low angles from the same probe position. With a standard S-scan, this is impossible without backing up the probe significantly from the weld. A very common inspection strategy is a standard S-scan from the front of the probe covering the ID, and a second S-scan skipping off the bottom into the cap for coverage. Two-group S-scan inspection, again, is independently configured and calibrated, and it also has to be analyzed independently or merged into a C-scan offline. The field testing and customer feedback from our beta testing and what we know of this up until now is that the compound S-scan is more productive in almost every respect, including ability to maintain near perpendicular orientation on a 30 or 37 degree weld bevel, which is very common in the industry. The ID coverage, and this is a 1 millimeter pitch, 60 element Pipe Wizard 1 probe with a shear wave 55 degree wedge that's typical of pipeline and large vessel inspections. We can see that use of the compound S-scan and a large aperture A-scan gives us 118 millimeters of coverage between the 40 to 70 degree beams. Looking at that same comparison in aperture using all of the elements in common for, using a single group of elements for aperture for all angles, in this case, much a smaller coverage on the ID of 81 millimeters. Taking that same thought process, skipping off of the bottom into the OD, again, one of the first benefits of multiplexing the angles across all the elements of the probe and wedge is that we're able to achieve this much closer to the weld. We are seeing the inspection from just slightly back from the weld toe of a 40 millimeter piping weld, and we're covering the first leg greatly in the high angle. The equivalent S-scan, traditional S-scan, would be more than 40 millimeters back from the weld for the exit point to achieve the same coverage, and a great sacrifice of first leg coverage. Were we to move the traditional S-scan farther in the first element start position here, it would be sacrificing coverage on the back side. So throughout this presentation and in some of the similar downloads for the recent webinars, we're going to see several aperture charts related to the new weld series probes, but also applicable to any probe and wedge in the Olympus catalog. Don't overthink these. These are very simply a chart that defines thickness versus probe aperture, which would be the equivalent of a single channel conventional UT size of the probe. The aperture is arrived at by multiplying the number of elements recommended by the pitch of the probe. And again, where traditionally we're only using apertures of 16 or 32 based on the pulsar limitation of the instrument, now there's going to be a reason to optimize that by using apertures of 16, 20, 24, 28, and 32. The aperture charts overlap in range. They're mostly separated to account for a range of inspection instead of just an individual pipe bevel, and that accounts for the range. But again, where A1, A10, A11 probes were used very commonly, and A2 and A12 for more coverage, the smaller 5L32, A31, and 32 probes will replace these and provide a much more efficient inspection with a better wedge. What is the benefit of buying a 32-element probe when the instrument pulsar is limited to 16 element configurations like the OmniScan SX? Without use of the compound S-scan, there's not much benefit to that. In this case, as a 32-element probe, we would either use traditional S-scan from the front, from the back, or both. And in most of those cases, customers with 16 pulsar instruments purchase 16-element probes like the A1 or A10. What our experience tells us is most of those customers where a small footprint wasn't essential for the inspection are greately benefited by a 32-element or 64-element probe. In the example below, the 5L32A31 compound that we see here on a 12-millimeter V-weld results in more coverage and a higher probability of flaw detection. To achieve this, the A-scans from 40 to 72 degrees are distributed over all of the elements of the 32-element probe. In a 0.6-millimeter pitch probe with the standard S-scan, depending on the wedge, there's about a 4 or 5 millimeter difference between exit point 1 and exit point last. In the compound S-scan, we see that's a much greater range, and the quality of the data for the characterization, the pixelization associated with linear scans is not present in the compound S-scan, as we'll see in some of our examples. The NDT Setup Builder, and specifically new version 1.1R2, is available on the Olympus website now. It was released recently, and functionality in this version includes the ability for the compound S-scan. Also included is matrix array support for TRL inspections of austenitic materials. Those are advanced probes used for austenitic. Both of those two features now are available in the NDT Setup Builder. This software requires a security key, and it is provided free with the price of an OmniScan MX2 module and MX2 base unit and current module, or it can be purchased separately. To use the NDT Setup Builder to create a compound S-scan, we're going to open up the software, and from our Tools menu, select the acquisition instrument. The selection of the instrument enables the module pulsar configuration to be defined, and that will prevent the user from creating a configuration or aperture that's not compatible with their instrument. After the acquisition unit is entered, the part is defined by selecting the material velocity, the material from the database, and the longitudinal and shear wave velocities associated with it are ingredient number 1 in a phased array inspection. The wedge delay and velocity wizards cannot correct a velocity tolerance error that creates an angle error in the material. For carbon steel inspections, we want to always use the default database velocity, and instead of modifying it based on a cow block, we want to validate that our angle error is within tolerance based on that same cow block. So all inspectors are using the same fixed velocity. The thickness is defined, the length of the width of the component or pipe, and then the weld overlay. The weld overlay has a series of templates for common industry weld bevels, including the radius inputs for the J and U groove welds associated with a lot of automated and vessel welds now that are very common. We define the 4 parts of the weld in the root, the land, the hot pass, and the fill. And it's a very easy, simple template to create general weld bevels for which to plot the beam and compound or traditional S-scan. After the part has been defined, you'll see 2 probe tabs, and we're going to demonstrate this shortly in the software. But the probe set tab allows us to define the probe. When we select add to probe, we are going to name the probe, determine what type it is, and these are all PA linear probes, meaning they're one-dimensional probes with the elements all aligned in the active axis for beam steering at low and high angles, but not passive axis steering. The wedge and probe family or housing is defined as a number, and once that number is selected, we'll see all of the applicable models within it. In the new weld series, like the A32, uses the same housing and wedges, but it comes in a 1 millimeter pitch large aperture model for thick pipes and vessels, and a smaller pitch, half the size of the element, twice as many of them, using the same housing and wedges. The wedge family is selected similarly, and we'll see a list of different wedges to include shear wave, L wave, 0-degree normal wedges. The IHC designates the scanner ports for the width of the wedge. One without the IHC would be a narrower wedge designed for manual inspection. After the probe and wedge is selected in the probe set tab, we will also define the orientation of the probe in relationship to the weld line or some other reference. And for a typical 2-sided inspection, that's done at 90 and 270 degrees. And we will select the pulsar number associated with element number 1 of the probe. In a single probe inspection, that will always be element number 1. If using a splitter, it will be typically 1 in 65 or 1 in 33, depending on the probe model. This information will all be built into the focal law that we will pass to the OmniScan. After the probe and wedge has been selected and the material defined, before we create the group, we want to move the probe index offset position to be within a few millimeters of the weld toe. Give yourself a couple millimeters, as the weld toe will vary a little bit along the weld line, and we don't want to be as close as possible because it will rub the dampening. For thicker welds, we will readjust this after we've seen the scan plan. But again, a big benefit of typical welds in the ANSI piping range below about 25 or 30 millimeters is that the probe is always done, the inspection done with the probe as close to the weld as possible. So this position here, and as defined in the OmniScan, is in relationship to the 0 millimeters on the index axis, which is normally associated with the weld center line. After the 3 parts of the hardware are defined, and by the way, any calculator for phased array, regardless of complexity or manufacturer, is always divided into 4 groups of parameters: the probe, the wedge, and the material. And those are all hardware parameters that can be measured. And the 4th part is group information, or the beam formation, that is software. The group tab is selected, and select Add Group. A new line with a standard default scan appears. We're going to rename the group something useful like SKU 90 or CAP or root or zone group. And we're going to change the scan type from the default sectorial to the compound. Previously, in the setup builder, there were 3 types: the linear scan, sector scan, and a single static A scan. And with the new version of the setup builder, we also now see the addition of the compound scan. The angle range was defaulted from 45 to 70. Most of Olympus's shear wave probes and wedges with common pulsar aperture configurations are capable of generating approximately a 40 to 70 or 72 degree shear wave beam. The size of the elements, the number of elements in the aperture, and the amount of attenuation through this wedge will all affect the ability to get the high angle correctly. The angle step resolution of typically 1 or 0.5 degrees. In the compound S-scan, it is the angle resolution here that will determine the total number of A-scans between A-scan first and A-scan last, which affects file size, scan speed, and most importantly, angular resolution on the weld bevel for improved sizing and better imaging and characterization. Unlike a traditional S-scan, in the compound S-scan, we are also going to define the first element of the configuration and the last element of the configuration. And in most cases, it's going to be the entire width of the probe or all elements within the probe. The 32 or 64 element probes are most beneficial for the compound S-scan. There's not much benefit in a 16 element probe for this inspection strategy, because to benefit from it, you would have to reduce the aperture below 16 elements, which even for a thin weld isn't desirable in most cases. In fact, in decision 1 that we're always going to make, based on the thickness or sound path of the target or weld bevel, is the aperture used in the compound S-scan. Again, with 16 and 32 pulsar instruments for most customers, that was automatically 16/32. Now, even though there's just a slight couple millimeters difference between some of these configurations, there is a benefit for coverage versus appropriate aperture versus ability to calibrate and provide a good inspection. And the example we're going to use in a couple of the data files and in our SUB is this example here of a 24 element aperture using 0.5 millimeter pitch, which results in an overall aperture of 12 millimeters, which is a very common probe for typical 12 to 20 millimeter thickness range. Okay, at this point, the component probe wedge have been configured and the compound S group has ready for focal law creation. Importing focal laws into the OmniScan allows us added value of advanced probes for which the OmniScan onboard calculator is not designed. This includes compound S-scan strategies, use standard probes, includes matrix array for austenitic inspections, and using a TomoView calculator. It also includes pitch catch and other inspection strategies as well. By putting the focal law on the SD memory card, we can import it directly into the OmniScan. So we're going to name the focal law to include the probe, 5L64, the wedge, N55S, the scan configuration of 40 to 72 degrees at 0.5 degree resolution, aperture, 24 elements, focus at true depth, 18 millimeters. This focal law is designed for pulsar 1 at a velocity of carbon steel 3240 meters per second. With a few common configurations on the flash card, most ANSI piping range can be inspected without having to go back and forth from the calculator. It's normal to develop a library of these and enforce them in the work procedure. So we want to remove as many decisions from the inspector as possible and move them to the work procedure so consistency and best results are optimized. These files that we create from the Setup Builder that we're getting ready to demonstrate, we're going to say to the law folder on the SD memory card under the user folder, which is everything relative to the user, not counting system files. If the law file does not exist on your flash card, create it under this directory. So we're going to demonstrate this up to this point using the Setup Builder V1.1R2. Again, from the Tools tab, we're going to select our acquisition, in this case a 32-128 instrument to enforce integrity of our configuration. We will define the part based on its material type and geometry. We will create the weld from a series of weld templates and populating the root, land, hot pass, and fill zones, and create our weld bevel. We'll go to the Probe Set tab and add our PA linear array probe. And again, a new functionality that you'll see in this version is support for dual matrix arrays for austenitic inspections. We have an upcoming webinar similar to this one on use of those probes as well. The probe we're selecting is from our new weld series probes, A32, A11, A2, A12 probes work very well with the same inspection strategy. We're using the 5L64 version of that probe, which is a 0.5 millimeter pitch 64 element probe. And we'll do the same for the wedge. Fewer probes using the common wedge family allows us a wider range of inspection without more hardware. And we're using the nominal 55-degree shear wedge in the I8C option for the scanner. We'll define it on the skew 90 position first, and we've configured this to be a few millimeters back from the weld, 9 millimeters here. So at this point, the probe, wedge, material have all been defined, and we can create our group formation. Before we go to the compound S-scan, I would like to demonstrate the back and the near and far side of the compound S-scan we're going to create by first selecting a 24 element aperture. This came from a chart based on thickness and probe and within the ANSI piping range that we will recreate in the Setup Builder. This is always decision one. The size of the probe or its beam relative to the weld bevel and sound path is our first decision. So the high angle, 70 or 72 degrees, we want exiting as close to the weld as possible without interference from this wedge dampening. Some of the Olympus probes and wedges allow a 16 aperture beam to interfere with the dampening here, and it's dependent on the operator to move it back a couple elements. This happens on the A12 and the A11 probes and wedges. So the new weld series was given a little bit more consideration regarding this. If this beam is interfering a little bit with the wedge corner or the dampening, the result is understeering and poor beam quality with calibration problems and trigonometry plot. So as close to the weld as possible or high angle. Then from the back of the wedge, using either a 40 or 45 degree for coverage, is going to represent our OD coverage on the skip. Defining the front part and the back part of our scan plan in 2 static A-scans is basically the same thing we're going to do with the compound S-scan. We need not do this static A-scans first. I just did that to demonstrate the idea. So I'm going to delete those 2 groups and create a new one, and it defaults to a standard traditional S-scan where all A-scans are being generated from the same group of elements. I had said our first decision is to select the appropriate aperture for the weld bevel thickness or sound path, and we're going to change our traditional S-scan to a compound S-scan. With selection of the compound S-scan, we can now define the front position, and we'll use the entire probe for the first element, and the last element position of 64 here. We'll reset our aperture to 24. Oops. Now, the number of A-scans that I would like inside is dependent on the resolution that I select for the angle coverage. So typical resolutions are either 0.2, 0.5, or 1 degree. This resolution, or the number of A-scans, is relative to coverage on the weld bevel. It's relative to our scanner speed and file size as well. And at 0.5, from a 45 to 70, gives us a very good angular coverage or resolution on the weld bevel and throughout the weld. We'll select a focal distance appropriate for the thickness and aperture. And at this point, our compound S-scan is programmed. Again, the scan plan is dependent on the user not programming angles outside the steering range of the probe, and almost all shear wave probes from Olympus or other manufacturers are designed for a 40 or 45 to about a 70 or 75 degree S-scan. Once this is configured, file, export, law file. So we notice that connectivity is disabled. Connectivity files include multi-group, phased array, and top groups. They include the weld bevel, and they're designed to import into the OmniScan. This functionality, like matrix arrays, like some future functionalities we'll see in the development of the Setup Builder, is a law file. The law file includes information for the beam and offset, but it does not include the probe and wedge information. So any change to the inspection parameters requires creating a new law file and importing it into the OmniScan. On the flash card, the law file, the SD memory card, the OmniScan version 4.2R2, which is new and on the Olympus website now, includes improvements for direct seamless import of focal laws from the external calculator. When we boot the OmniScan and select File New from the File menu to clear out all existing configuration, calibration, and group information, now we can select Load Law File directly from this menu. We need not turn off Probe Auto Detect or do any other task in the software prior to focal law import. Select Load Law File. And the previous version, 4.1 of the OmniScan software, in fact, all of the modules and generations of base units, modules, and software for the OmniScan MX2 and SX are compatible with the compound S-scan. It's just been made a little bit more seamless and easier using the latest versions. For people not upgrading to 4.2, for 4.1 users, there are 3 conditions that must be met to be able to import a law file. And condition 1 is Probe Auto Detect must be off in the probe part menu. Any 128 element probe must be selected from the database. and the auto focal law needs to be in the off position in the focal law menu. When you select open on the law folder, we'll see the contents of all of the law files in the law folder under the user folder on the SD memory card. Again, a law file is a very simple text file that includes the offset and beam information and delay information for each element, but contains no probe or wedge information to recreate or make a change. Select Load File, and the OmniScan will load the desired law file. It's common that you'll receive possibly one or two messages related to the voltage or wedge delay and filter. These are normal upon importation of a law file. All wedge delay, calibration, TCG, and filters are reset. Depending on the module that you selected in the Setup Builder, you could also get a voltage warning message. Just select OK, and the file will load normally. And when the law file has been imported into the OmniScan, all functions of your normal work procedure for setup are still valid and normal. We'll create the part thickness in the setup wizard and create the weld overlay as well. We'll adjust our UT settings and display as a normal weld inspection procedure. So we'll adjust our pulsar for the import focal law will always set the voltage to 40 volts or the low setting. So the recommended voltage for 0.5 to 1 millimeter pitch probes for weld inspection is the high setting of 115 volts. The probe frequency and pulse width are built into the focal law, but they can be overridden in the OmniScan user interface to fine-tune the pulse width or to achieve probe frequency that wasn't in the database. So these are configured as normal. Anyone trained in use of the OmniScan, once the focal law is imported, they will see something very similar that they're used to seeing in their traditional S-Scan, just with much, much more coverage and range. One difference in use of calibrating the compound S-Scans is there's a much larger difference between the wedge attenuation for A-Scan first, low angle, and A-Scan last. So the gain compensation in the sensitivity wizard that aids in accurate calibration and increases the dynamic range of the S-Scan is best set from the default value of 2 dB per microsecond for S-Scans to 0.5. And select Apply, and we'll see a very similar calibration curve across the S-Scan. In this calibration wizard, the limits for calibrating it are focal law first and focal law last cannot be separated by more than approximately 20 dB, which is about 95 to 5% amplitude. And the higher we can calibrate, the more accurate the correction as a result of the window will be. Regardless of your configuration or how you go about choosing aperture, focus, and angular range, a very good tool, which we use often, is the ASTM 2491 beam validation calibration block. This is a specification that doesn't give a go, no-go or a compliance tolerance, but defines some tools for determining the beam limits of any given setup. It's extremely useful for putting the probe at the inspection position on the index axis or offset position and simulating the weld bevel through your inspection. There's a row of 30-degree 1 millimeter side drilled holes, and by putting the probe at this same inspection position, I can see the quality, resolution, characterization, and inspection sensitivity across the entire area of interest. On an inspection like this, we could expect to see very precision sizing capability on the weld bevel and throughout the weld for volumetric flaws. We're looking for a velocity, angle, and exit point validation that will result in correct trigonometry. If the probe is where the software thinks it is, and the side drilled holes or notches of any cow block are plotting at the correct position in the weld overlay, it's an indication that our trigonometry is going to be accurate, resulting in a very good inspection. This validation is extremely useful for visualizing and optimizing probe parameters, such as the benefit of using a higher frequency, the focus of a particular inspection, the benefits of more elements in our aperture, and our selected angular range for any given weld bevel at any given offset position or sound path. After you do this a couple times using a standard S-scan and a compound S-scan, the benefits are very obvious. It is impossible to achieve this level of coverage and clarity without use of a compound S-scan when using a 0.5 or 1 millimeter pitch probes of 32 and 64 element configuration that are very common in the phased array industry. So in this block, on the same block that we see here, ASTM 2491, from any of these different positions, as I scan this slightly forward and slightly backward, what it allows me to do, it allows me to visualize the calibration targets before my area of interest, at the weld fusion zone, and inside the weld bevel. On a properly calibrated inspection, we want to see correct depth, time of flight, and characterization, amplitude within a dB or so of the intended calibration, typically 80%. And this gives us a very good idea of what type of inspection we expect. Okay, as I change this slightly, moving it forward and backward on the cow block, I've also recorded this clock scan with the A-scan envelope on. The A-scan envelope readings for the -3 and 6 dB drop show me the vertical height sizing window, or also called the echo dynamic, that affects sizing on the weld bevel or at any position inside the weld. The decision to use a 1 degree or half a degree or 0.2 degree inspection is directly related to this. Lower frequency probes or unfocused probes from farther distance will have a much larger number here for our 3 and 6 dB drop inside the envelope window, and that's a consideration for our scan plan. For most of the new weld series probes, using 5 megahertz probes as close to the weld as possible, they provide a very high resolution block. And again, the other thing this block does is it separates pretenders from contenders. And it also helps us identify extraneous adverse echoes from the wedge and housing and indications as well. It's very, very useful, and I highly recommend it. These are available in carbon steel and common austenitic materials as well. And for phased array, they're a very big help, especially the 30-degree weld bevel. From several different orientations, we can predict the results. The data sample below is a two-sided inspection of a 12-millimeter V-weld. Notice the crack resolution coverage range from both sides of the weld, and this is using a 0.5 millimeter pitch probe and a 32-128 instrument with the appropriately programmed aperture. This results in a much better inspection than the small 16-element A1 and A10 probes and wedges are capable of. And it also provides a more optimized inspection than that of the A2 and the A12, which are the most common big element pitch probes, also compatible with the compound S-scan. We're looking for absence of wedge echoes, clear coverage on the ID, on the OD to cover the weld and our heat affected zone and area of interest. Most data that we see at Olympus technical support is probably 3 or 6 dB more sensitive than the referencing code requires. So we'll see here a light blue 2 to 5% ID roll. Fusion flaws will be in the 100 to 200% amplitude range, and small cracks from the 50 to 100% amplitude range, very typical. This two-sided coverage uses the same number of focal laws as a traditional S-scan, but much more coverage. If we increase the angular resolution to 0.5, we will use the same number as 2 groups on each side of the weld, but it's a much more efficient inspection. And most importantly, we're not backing the probe up for coverage, and this single setup with a long enough TCG can be adapted for use on other weld bevels by just adjusting the UT parameters. The ability to detect flaws and size them with precision is dependent on many factors, including the probe frequency and aperture. The sizing precision is improved by use of higher frequency probes, multiple focus strategies and multiple group, multiple line scans or raster scanning, manual prove up with probe in hand, TOFT, supplementation, and increased UT point count, which is the same as the low compression factor on the A-scan. And again, amplitude-based inspections for detection, a very different requirement than precision sizing typical of a fracture mechanics type of inspections. If you are an ES beam tool owner and fan, like those of us at Olympus are, this is called the linear spread beam set in the ES beam tool. The ES beam tool allows a much greater functionality for importation of drawings and pictures, creation of complex weld joints and one-sided inspections of all different types. This linear spread beam set can be configured and plotted in the ES beam tool and programmed in the Setup Builder to import the law file necessary to create it. And again, they call this a linear spread beam set, and it is the same functionality as the Olympus compound S-scan. The aperture charts that you'll see in the information you get with the download of this webinar will include the data files, this presentation, and some probe recommendations. The A32 and A31 weld series probes take into account the beam size, the beam exit point in the wedge on typical welds, the sound pass through a typical weld of a given thickness. The limits of any one probe and wedge will be pushed by the OmniScan customer base, and the recommendations are estimates that can only be validated through trial and error under actual inspection conditions. Lack of a 1 millimeter pitch probe, a large aperture probe, typically used with a 32 pulsar instrument, is problem number 1 for most companies inspecting thick weld bevels, to include the EPRI fossil sizing test and ASME 8 vessel qualifications for ASME. The charts don't list any specific angular range focus, don't differentiate if supplemented with TOFT, and make no specific recommendation as to exact scan plan. It's a starting point for probe versus aperture, and it is no coincidence that the recommended PA aperture is similar to conventional UT probe size for a given thickness. And again, these overlap a lot. I don't want you to overthink them, but the key point is, instead of apertures of only 16 and 32 elements, with the use of a compound S-scan, we will benefit from apertures of 20, 24, 28 as a compromise for coverage versus orientation to the weld or position to the weld and acoustic results. The advantage of smaller pitch, larger element probes is that they are a larger wedge footprint, not so optimized for thin components. They don't have the large aperture for large vessels, but within the range of approximately 10 or 12, 25 or 30 millimeter, they provide the best overall inspection for the widest range of welds. Additionally, it provides the most versatility if the customer is limited to only one probe or job and a narrow thickness range. The last example, and again, you'll receive a couple of files with the download for this webinar. We see in a typical weld inspection, a one-sided, our same 12 millimeter weld bevel. This demonstrates the benefits of a 4.2 R2 in that now we have ability to use software gain. So our ability to raise and lower the amplitude minus 6 dB and plus 6 dB for fusion flaws or for cracks, for small tip diffraction now is available directly in the software. We can set the reference sensitivity and scan 6 or 12 dB hot and reduce it in analysis mode. This is new functionality for 4.2 R2 and very beneficial to the compound S-scan. So I want to thank you for attending our webinar. Again, all of these tools are available in your existing probes and wedges. Contact your local Olympus salesman or distributor for an on-site demonstration, and we will see you sometime in the near future for our next webinar regarding an update to the dual matrix arrays for austenitic weld inspections. I'll turn this back over to our moderator, Greg, and thanks again for attending.
Thank you, Chris. On behalf of Olympus, I'd like to thank all the attendees for joining us today and Chris for his expertise and participation in today's event. We hope this material presented was informative and useful. This webinar will be archived on our website at www.olympus-ims.com. Everyone who registered for the event, whether you attended or not, will receive a follow-up email with links to the archived presentation, as well as a link to the data files that Chris was telling you about. Thank you again. That's going to do it for today, and we'll see you again for the next Olympus webinar.